Okay, so let us continue. So we finished module of video transmission issues last time. Sorry about that. Rains and apparently it goes haywire. Let us hope this doesn't happen today. Anyway, so we finished. We basically spent one lecture, a short lecture, on the quadratic forms, symmetric bilinear forms, basically over general fields, and that sort of was the spectral theorem over a field of characteristic not 2. And the idea is that actually the spectral theorem holds much more generally if you restrict the field to be complex or real numbers. In that case, it holds for all kinds of matrices, namely matrices such that their adjoint commutes with themselves. So first of all, how does this notion of adjoint arise? And that notion arises in the context of these vector spaces over R or C, finite dimensional such spaces, because they are equipped with something called an inner product. And you can take dot products or inner products, you can do orthogonal maps, Cauchy-Schwarz, and so on. So let us start with inner product spaces. That is where we will spend this lecture and also the first lecture of next week. Yeah, pretty much. And so next lecture, towards the end, we will start with adjoints. That will go on for, so there are 4 more lectures in the course. So this lecture and next lecture will go towards inner product spaces. The third lecture remaining will go towards adjoints, and the very last lecture of the course will discuss the spectral theorem. So that is the goal. Okay. So without further ado, let us start. So inner product spaces. Okay, so so these are the vector spaces with something called an inner product. So an inner product is a map. So definition. Okay, so throughout, this is a big disclaimer. The rest of the course, I should discuss it for the rest of the course. Meaning in the next 4 lectures, this lecture and the next 3, the ground field will always be the real numbers or the complex numbers. Okay, so that is always. So I will keep saying F because the results hold equally well over the reals and complex. And the point is, it's usually better to keep those separate because something is linear or it's conjugate linear, that kind of thing. But the results will be only considered over real numbers or complex numbers. Okay, great. So let's start with the definitions on inner product. So from now on, whenever I say F, I mean either the reals or complex. Okay, so definition. An inner product on an F vector space. So the vector space will be, I don't say finite dimensional, okay? It can be infinite dimensional as well. Vector space V is a map just like a bilinear form. It's basically like a symmetric bilinear form. Okay, that satisfies the following properties. Satisfying. Okay, so 1. So it's additive in the let's say it's linear in the second coordinate. Okay, I will say it in the way that it differs. So let's see. So if you look at basically C, a V times W plus W prime, and this is VW plus VW prime. I will put in the for all later on. This one is the tricky one, CV comma W. So if you have a scalar times a vector, then of course you hope the dot product comes out with the same way, right? So it's C times D comma W. This is false. This is not true. If the ground field is the real numbers, it is true. If the ground field is the complex numbers, this is not true. And that's the whole point of this point. That's why I'm saying it here. It's C bar times this. Okay. So in the first coordinate, it is antilinear or conjugate linear. Okay, great. The third part I think is just the swapping. Oh, no, fine. Maybe I don't want to say this yet. Fine. I'll say that later on. So the second one is, I wrote down the properties as opposed to definitions. So VW, if I want to swap W and V, then is this equal to VW? And the answer is no. This is equal to VW, and then you take the conjugate. So this is the property from which we will derive that next thing. Okay, the third one is the scalar, I guess. I could have done the other way, but V and then CW. If I have the scalar in the second coordinate, then indeed it is C times VW. Then that scalar in the second coordinate comes out, linearity in the second coordinate comes out, and the final one is what one calls positivity, namely that the inner product of any vector with itself, if V is non-zero, then yeah, that's all I need to say. V comma V is strictly positive. Then this is a scalar. It turns out to be strictly positive, meaning or it belongs to zero infinity. Okay, that means it's a real number. It's not just a complex number. Remember, f is either R or C. So whatever this is, it's a real or complex number. So it's a complex number. But what we are saying is, if you take V comma V, then it is in fact a positive real number for all V not equal to the zero to the origin. These are the four properties, I think. And now I need to tell you the disclaimers, the quantifiers. This is, let's see, what are all there for all V and W in the vector space, and this W prime also. And the scalar is in F. Okay, so that is the definition of an inner product. Okay, fine. So now let us write down some basic properties. Our examples first. First properties, then examples. Lots of examples. So properties. Okay, these are too many to list, so I just wrote them down. Oh, good. Even this one is wrong. That's fine. Let's keep that one here and then the other one there. Then it's linear in the second coordinate. So let's see. So then here conversely I should say V plus V prime comma W equals V comma W plus V prime comma W. Am I going to prove any of these? Why not? Let's prove this one. So how do you write this? Well, you use properties 1 and 2 only, right? So the left hand side, first of all, I can swap. So I get W V plus V prime. But then I have to put a bar. Fine. But now we know that by property 1 over there, this is WV, this scalar plus WV prime. And it's the whole thing conjugate. But the conjugate of a sum of two complex numbers is the sum of their conjugates. So I can put that. And now I can swap back using the property 1. So first of all, this one was property 2. This one was property 1. And then I again swap using property 2. This is W, V comma W without. So then I take 2 bars. But the double conjugate is itself of any complex number. And similarly, V prime comma. Okay, so these are sort of very simple such properties. Okay, property 2 is, well, this is already done. The property 2 is this one. If I take CV comma W, then this is equal to, well, again, you can do the same thing. I can take W and then CV on this side bar. So the C times WV whole thing bar, the C bar times WV bar, but WV bar again is VW bar. So you just get it. Okay, so that you can check why this is true, that's obvious. And then this one, of course, you should check that. So we said that VV is bigger than 0 for all V non-zero. But what about the other vector? What about the 0 vector, right? So of course you have to say that. I should have said that somewhere here. Maybe I'll do it this way. I'll call this C and D because it corresponds to 3 and 4. And for B, I'll just say that if F is the real numbers, So this is for complex numbers. So F is the real numbers implies WV equals VW. Because there is no conjugate, that whole thing is real. The third one is this one, and the fourth one similarly 0, 0 is 0. Why is that true? That is true obviously because maybe I'll give the homework now itself because we may as well use it right now. Where is the homework? This homework, I should just put it right now. Give me 1 second to add this in here. So good, this one, and this is V plus V prime. W and then D is 0 V comma 0 V, and then homework. Okay. Actually, this is not really homework. This is property E. Okay, this is homework, but this is just extremely trivial homework. Okay, so property D is this. Why is this true? Again, this is literally like the original field axiom statement, right? You can write down 0V. So let's just, I write down the proof in this assertion itself. The first of all, I can write 0V is 0V, 0V plus 0V. And now by the property 1 here, you can write down, this is from the axioms of vector spaces. So this is the additive identity. So I'm really going down to the basics of additive identity and so on. Property 1, this says it's 0, 0 plus 0, 0. So now I have something equal to 2 times itself. I can cancel one of them and get that in C. Okay. But there's also a property E, which is, I'm going to say is homework. It's a trivial homework. And the home property is literally that if, suppose I have any vector, if V comma V is 0, meaning if V is has 0 inner product with every single vector, then V equals 0. Okay, and in fact I can even say the same thing here. Anything comma 0 is 0. So I take any vector here. I didn't even need to say that was 0. This is V comma 0 plus V comma 0. So basically I take any vector in V, like a vector V0, then V0, 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 and so I can cancel. Right? So that's the converse of part E, but they are all true. Okay. Okay, so that's that. So these are some of the basic properties of inner products. There's really nothing to prove there. But now let's do some examples. And as I said, I will talk about not just finite dimensional examples, but infinite dimensional ones as well. Okay. I think the first one is Rn or something. Cn, yeah. So again, like just like Rn, you can talk about Cn. It's the same thing. So the first one is Cn, and yeah. So basically, let's call this A, and V equals Rn over F equals R, of course. This is over F equals C here. Okay, and here we know the inner product. V transpose W. That's an inner product. It's clearly linear in both of them and all the properties are satisfied. Well, the same thing happens here, but except for the fact that you have conjugate linear in the first one, right? And you also want that the V transpose V should be positive. You want this axiom to hold. Well, so if you do just V transpose W, that will not hold. What you really need to do is you need to do V transpose bar W. Okay, or another way to call it is V star W. And the whole point is the star is exactly this adjoint map that we are going to see next time. So for now, yeah, it's this one, and the special case is this one. Okay, that is the prototypical example of obviously here I should say n bigger equals 1. This is the prototypical example of an inner product space. Right? Okay, great. And again, you should see, right, that if you take the C in the first coordinate, then you get C V transpose, but there is also a bar, and so a C bar comes out, which is what we want. We want a C bar, not a C, from the first coordinate. Okay, the second one now is, okay, obviously, another obvious example. If V is any inner product space, then you can take any vector subspace of this space, and that will satisfy the same axioms. So you can easily check. Then so is any subspace of V, or every subspace of V. Okay, next. So I think these were the finite dimensional ones. Now I should say the infinite dimensional one. Yeah. How about V equals L2 of F? What does this mean? This is defined to be the sequences A1, A2, AN. It goes on, infinite sequences, such that AI or AJ belongs to F for all J, or let's say AN belongs to F for all N, and summation n equals 1 to infinity mod AN square, because mod AN is a real number, so mod AN square is finite, and the summation of this has to be finite. That is the condition for L2. These are square summable, as we call them, square summable sequences, or non-square summable sequences of complex numbers. Now here, I need to, so okay, at least over here I told you what the definition was, and here the definition in any subspace, the inner product is the same inner product inherited from the bigger space. Here I need to tell you the definition of the inner product. That definition is the following. It's basically the same as this, or yeah, as this. Under is an inner product space under the inner product of a sequence AN and a sequence BN is the summation n goes from 1 to infinity AN bar BN. This is like taking the transpose of the first coordinate. So I'm taking the bar. Okay? AN bar times BN. That's the definition. You can check that this is all very good, except for the fact that it's defined at all. Why is this defined? Once it's defined, modulo the convergence issues, then everything else, all the other properties are fairly straightforward. So some summation, or you reorganize summations and so on. That's not very hard. Okay, but that's, I mean, these are of course calculus arguments, so I'm not going to do much about that. But basically the question, the big question really here is, why is this even defined? Is this inner product well defined? Okay, that's the real question. And the answer turns out to be, well, let me write out the formal lemma and give you the formal reason. So basically all you know is that you know that summation AN square is less than infinity, mod, and summation mod BN square is less than infinity. You want to ask if why is this summation convergent, right? So, let's do that. We will not only say that it converges, but we will give us upper bound. It is at most so much. Lemma. if An and Bn are elements of this field, if this vector space, meaning that these things happen, then the dot product makes sense. Summation An Bn bar converges in the field, meaning in R or in C. And therefore you can make this definition and then everything else one can show goes through, which I'm not going to show because this is a linear algebra class, not an analysis class. Okay, so why is this true? And the quality is okay. Let us hope today we don't have internet issues. So why is this true? Basically, it's true because of the Cauchy-Schwarz inequality. So, in fact, this is a complex number whose absolute value or modulus square is less equals summation mod A n square, summation mod B n square. And remember, both these summations are finite. So the right hand side is finite, left hand side is finite. And so without the absolute value, that means this number lies in the complex disk around the origin of radius at most the square root of this. And the reason why this is true is by the Cauchy-Schwarz inequality. And the point is, we will prove this later. So rather, this will almost be a circular argument, right? Okay, let's do this slightly better. I'll say it slightly more carefully, right? So let me take the summation up to a finite stage. In that case, this is true because this is true by the Cauchy-Schwarz inequality in f to the n, in f to the capital N. Okay, and the point is f to the capital N, there is no question about convergence issues. So therefore, f to the capital N is indeed an inner product space, and in that inner product space, this inequality holds. But in turn, this here is less equals. Clearly, a partial sum of some positive numbers is less than the full sum, which means n goes from 1 to infinity times bn square mod square n goes from 1 to infinity. So for every finite n, this finite sum mod square is less than this guy. That means you have a countable set of such. So that means you have a countable set of such complex numbers which lie in the disk around the origin of radius square root of this. This is a finite number. So that means there is some disk of some finite radius. So that this radius rho or r square equals this thing. This whole thing is r square. Right? Now there are the summation for n equals 1, n equals capital N equals 2, capital N equals 3, capital N equals 4. You have something like this, right? Well, the point is that this is a compact set. Again, this is, as I said, an analysis argument, so I'm not going to write this out. But this is a compact set. There's an infinite sequence in it. Therefore, it must have a convergent subsequence. And the limit point of that convergent subsequence is exactly what we defined to be, is what this is defined to be. So anyway, so this is how you say it. Now I'll just say now let n to infinity and use that the disk in the complex plane around 0 and r is compact. But anyway, as I said, I'm not going to actually sit around and proving this. But the Cauchy-Schwarz inequality in f to the n, we will actually prove, because we will actually prove it in any inner product space. And now once that is proved, that can be used to prove that this converges Therefore, this is in the product space. Therefore, in it Cauchy-Schwarz holds. So I can't use Cauchy-Schwarz in this space to prove that this is in the, to define an inner product here, because that is circular reasoning. But I can use Cauchy-Schwarz in f to the n. To do that, then take limits, and now this is defined. Once it is defined, Cauchy-Schwarz works here as well. So that is the way to do it. So let me just write something here. Okay, fine. So great. So that is that. So that is one infinite dimensional, in fact, a countable dimensional space. Now let me say something which is, I believe, probably no, it is also still countable. Anyway, I'll give you this is a discrete version. I'm going to now give you a continuous version of the same space. So example 4 is when we talk about functions defined not on countable set but on the whole interval. Let's see. So V equals L2. Let's say 0, 1. Okay, I believe it's a closed interval. Blah blah blah. Yeah, why not? Okay. Oh, and I must say F also, of course. And what is this? This is defined to be the set of all F, let's say from 0, 1 to F, which are something called measurable, but I mean, don't even worry about this. Some kind of nice function. You can think of them as continuous functions. Actually, why not? Let's just say continuous functions. If you really don't want to think of measurable, just think of continuous functions. But the point is not. The point is what they satisfy is L2. And they satisfy exactly the same kind of thing as this, such that the integral from 0 to 1 of fx is a complex number possibly, so mod f of t square dt less than infinity. And once again, one can prove that, I should have said under, this is an example under f comma g is defined to be the integral from 0 to 1 f of t bar g of t dt. And once again, you can show that this quantity, whatever it is bounded below, is bounded above by basically the same kind of things. By f, the square of this, the absolute value square of this is bounded above by f comma f square g comma f comma f g comma g. Okay. Again, that's the Cauchy-Schwarz inequality, which we will show. But you can again show that first of all that holds, and that is why this makes sense. Therefore, it is in the product space, and therefore here again you have the Cauchy-Schwarz inequality. So anyway, the point of these whole examples is that these are all infinite dimensional spaces. So I'm not really requiring V to be finite dimensional to be an inner product space. Okay. Okay. So now I didn't define the norm somehow. So let me now define the norm and orthogonal. So now we need two more definitions. So now again, V and is an inner product space. Let's say over the field F, which is the real or complex line. Okay, so definitely two definitions. The norm of a vector. What is the norm of a vector? Well, as we saw, V comma V, if you take the inner product of V with itself, then it's a non-negative real number. It's either strictly positive or zero, right? When 0 comma 0. So that means whatever this non-negative real number is, it has a square root. And that square root is defined to be the norm. And the second is we say that V and W are orthogonal in this space. The vectors are orthogonal. Actually, fine, I'll give a third definition as well. Third is that an entire set is orthogonal. Okay, it's already there. Fine, we'll do that later. Orthogonal if V bracket W is 0. is the scalar 0. Notice that I have not said W and V are orthogonal and V and W are orthogonal, because if I take W bracket V, then I get the conjugate of 0, which is still 0. That's fine. Okay, now for some more lemma or another more basic properties. V and this thing is an inner product space. Okay. Some of the basic properties you already saw. Maybe I should call this lemma. Okay, so actually this should not be called a lemma. It should be called a proposition, because now we will prove this Cauchy-Schwarz inequality, and we will also prove the triangle inequality. So one, first of all, is that the norm of a scalar multiple of vector is, again, so first you take the norm, but you have to also multiply by the absolute value. So for example, remember the norm is really like the length of a vector. It's exactly that. So if you take minus 2 times a vector, means you take twice the length and you orient it in the opposite direction. The length is still double the length. It's not minus 2 times. So that's the mod C. Okay, so mod C times B for all C in the complex or real numbers and B in D. That is obvious. Okay, second. The second is called. So now there are 3 theorems, if you will, with names. Okay, so the first is. I should have said. V. Say V perpendicular to W. Right? Of course, the notation for orthogonal is V perpendicular to W. So the theorem here is called, as you know, Pythagoras theorem. If V is perpendicular to W, actually it's if and only if. I should have said that. V is orthogonal to W if and only if V plus W square equals blah, blah, blah. I think this is true. No. This is true if the thing is the real numbers, not for complex numbers. I could put plus minus and then I'm done. Fine. So you've already seen Pythagoras theorem in the usual setting, right? If V is perpendicular to W, then if you have 2 vectors V and W, then they're orthogonal, then this V plus W norm square is V equals norm square V plus norm square W. That part we've already seen. That part we all know. This one is going to be slightly different. I'm going to say V is orthogonal to W in V if and only if, norm square of V plus W equals norm square of V plus norm square of W. So, equals norm square of V minus W. Is this true now? Or maybe it's true for V plus I. Okay, let me not say all this. Okay, let me say that this is true, and the converse is true if it's real. I don't want to think about this right now because we don't have time. And the converse holds. If F equals R. That is the first of the 3 named conditions. Okay, fine. The third condition, the second named condition, the third part of the proposition is the Cauchy-Schwarz inequality, which says exactly this. So I'll just see that. And And some people also add the name Bunyakovsky. Bunyakovsky. Cauchy-Schwarz inequality or Cauchy-Schwarz-Bunyakovsky inequality, which says that V, W, take any two vectors in any inner product space. This square is less than norm square of V, which is this, times norm square of W, which is this. With equality, it even tells you when you have equality. If and only if and only if V and W are proportional. So either W is any vector V is 0, or V is any vector W is 0, or they are scalar multiples of each other. So let's say V and W. But there is a way to say that in terms of linear algebra. It is that they are linearly dependent. Okay? And the fourth one is called the triangle inequality. And again, that is well known to you guys. It is that if you take any triangle, not just perpendicular, but V and W, the length of V plus W is less equals. So the length of V plus W, the norm, less equals norm V plus norm W. And I should probably put quantifiers everywhere, but I mean, I could just say, I should maybe add a quantifier here before part 1. Okay, so say so V and W are just arbitrary vectors. Then, yeah. Okay, same thing here. And equality happens if and only if. You can do equality here as well. Again, if and only if V and W are linearly dependent. Okay, great. Okay, let's start to prove these things. So how do you prove it? So let's see. So the first one is, the first one is this one. The first one is just trivial, but I'll say it anyways. Okay. The first one. So let's just take the squares on both sides. So this is a useful point to consider, to remember. Whenever you're trying to do stuff involving norms, an easier thing to do is to do stuff involving norm square. And why is that? So because norm square of any vector is just the inner product with itself. And inner products are bilinear. So you can add, subtract, rescale. Whereas in the norm, you can't really do that. So let's take the square on both sides. So let's just start with this thing, norm square C dot V. Well, as we saw, this is C dot V and C dot V. But now the scalars come out, and we have seen how the scalars come out. The first scalar comes out as C bar, and the second scalar comes out as C, and you get V comma V. But what is C bar times C? This is norm C square times V comma V. Sorry, I can even put norm square V here. And you see, this C times V is a non-negative number. This norm is a non-negative number. So if you take the square roots, of course you get non-negative numbers. And therefore you're done. Now take square roots. Okay, second, Pythagoras theorem. That is even more trivial. Or maybe not even more trivial. That's just part of this equally trivial. So let's see. So let's write down V plus W square. And this is V plus W and V plus W. But now, since V and W are orthogonal, okay, let's write this down. This is V comma V plus V comma W plus W comma V plus W comma W. So now since V and W are orthogonal, these two vectors are 0. And so you just get VV plus WW, and that is exactly equal to the right hand side. Okay, conversely, suppose I know that these two are equal. That means that this plus this must be 0. So by the same calculation, if this is equal to this, then by this calculation, by the above calculation, those two terms add up to 0. But over a real numbers field, over the reals, these two are actually equal. Because you take conjugate of a real number, you get itself. What you get is 0 equals as I said, because it's over f equals r, this is equal to twice VW. Even if 0 is equal to twice VW over the reals, you can divide by 2 and so on. Okay, the next one is part 3. That's Cauchy-Schwarz. That will take a little time. Okay, I don't have the patience to do this. I'm going to start a new pen. Black pen. Okay, so Cauchy-Schwarz is that. So we'll do it slightly more carefully. I'm going to take a constant multiple. I'm going to look at the following. So this is a very clever trick. I guess you see it when you do Cauchy-Schwarz. 1 second. What you do is you look at a constant, you look at the linear combination of V and W by the axioms. You know that 0 is less equals the norm square of any vector for any scalar C. I'm going to choose a very specific, very special scalar here. Oh God, I should have said something else first. Right? So before this. So okay. I want to do the Cauchy-Schwarz. Fine. Suppose my vector V is 0. Then 0 bracket anything is 0. We know that. So this hand side is 0. This is also 0. So 0 less equals 0. That's obvious. Also, there in fact the less equals is an equality because both sides are 0. And in that case, indeed 0 is proportional to any vector. So if V is 0 or W is 0, then the result is easy. Immediate if so first of all, you get that out of the way. Now let's assume that both are non-zero. In fact, you just need that one of them is non-zero, but let's assume both of them. Now say V and W are both non-zero. Okay, and now take a scalar and compute. Let C belong to F and compute. And so what I compute is the following. I look at a linear combination of V and W. And of course, that will have a non-negative norm square. I'm not saying that that combination is 0. Well, we want to prove it's 0 eventually, but fine. At least it is a non-negative length square. So 0 less equals V minus CW, V minus CW. But now expand this out just like we expanded out this thing here. So you get 4 terms. Okay, and of course, with the C here, you will get an antilinear. So this is equal to VV plus CW as we saw just now in part 1 was mod C square norm square of W or let's say WW. And then you get minus C. So first of all, the CW comma V is C bar W comma V minus C V comma W. Okay, and now I'm going to convert this again by taking another bar. So it is norm square V is mod C square norm square W. And then let's see, which way do I want to say it? Okay, fine. Minus C times VW, that is this term here, minus C bar times VW bar, which is this term here. But now if you add a number and its conjugate, you get 2 times the real part. So here is where you need to, of course, know what are complex numbers and what is the real part and so on and so forth. Okay, so far so good. So this is a calculation. So far all we have said is that this expression is non-negative for every choice of C, scalar C. So now I'm going to do the first. And the scalar need not be real, the scalar can be complex. Now I'm going to cleverly choose my scalar to be the conjugate of this guy. Okay, this is true for all C. Okay, so choose C equals W comma V. Then what do we get? Then we get 0 less equals mod norm square V plus W comma V. So mod C square is W comma V square, sure, norm square W, minus twice real part of C is W comma V, this is V comma W, I guess that's it. Oh, oops, sorry. This is horrible. I forgot to divide. W comma V by, I believe it must be W comma W. Remember that since W is non-zero, I can divide by this. And now what about here? Here also I must have W comma W. And here I should also have, I am taking the norm square, so this must be square. Great, now we are finally correct. Sorry for the mix-up, I forgot to divide by this. Okay, but now let's look. This is norm square W, that's just WW. So one term here cancels with this. And what you get is this is norm square W comma V. This is also the same thing because these are two are conjugates of each other. So any complex number times its conjugate is a norm square of either this number or that number. It's the same thing. So this is equal to norm square V, okay, plus WV VW over WW minus twice the same thing because you see this is real. If you multiply any number with its conjugate, that's a real number, it's a positive non-negative number, divide by a positive number, that's still real. I'm stopping putting underlines. But you see, that means I'm adding this thing and subtracting twice the same thing. So this is equal to norm square V. Let me switch back norm square V to V comma V. Minus W comma V. Let's just, okay, now I just put it back. I should just have said that instead. My mistake. Sorry. I should have said this. I should have said it in the form that I want to prove Cauchy-Schwarz. So this is V comma W norm square divided by WW minus twice. I don't need the real part, and I have the exact same expression. And therefore, that is equal to VV minus V comma W square divided by W comma W. And this expression is bigger equals 0. But that's exactly Cauchy-Schwarz. Right? Take this number to the other side, multiply by the denominator, and you get exactly this. So you get the inequality. This proves the inequalities. What about the equalities? Because ultimately that is part of the theory. Okay? Where is equality true? Well, beyond this extra point, everything else was just an equal sign. Everything else was a calculation. So only time it's going to be true is when this inequality, the original one, is an equality. But how can 0 equal the norm square of any vector? That vector must be 0. Where C, of course, is this. This. But either way, the moment V minus CW is 0, it means V equals that multiple number times C. V equals CW for some C. You can check it by the way. So this part, I only proved one implication. If this happens, then that is true. Sorry, if this happens, then this is true. But conversely, if this happens for any arbitrary C, then that C must be that. Well, then you just take that the Cauchy-Schwarz holds. Fine. So that is that. Now the triangle inequality, similarly, again, you want to prove this thing with the norms, but as I said, the trick is to square both sides and prove that because that involves norm squares. Let's check what happens. Okay, so this is part 3. Squaring both sides. We have the left hand side square. Okay, is V plus W norm square. So it's V plus W bracket with itself. Now again expand in 4 parts. VV plus WW plus VW. And since everything is non-negative, I can take absolute values here as well. Okay. And now by the triangle inequality for real numbers, because these are all scalars or complex numbers, so the triangle inequality for complex numbers, triangle for C or for F basically, R or C. This is S equals VB. I don't need to put absolute values because this is a non-negative number, norm square plus WW plus VW inside absolute value plus WB. Okay. So and now I use Cauchy-Schwarz. Actually, maybe the triangle inequality has some delete that statement. I just want to prove the S equals. No. Let me not put these absolute values. Look, these two numbers are conjugates to each other. So when you add them up together, all you get is the real part. You get twice real part of V and W. That's fine. And there is no triangle inequality here. This is still an equality. Everything here is an equality. Great. Okay, well now what is this? Another way to write this is norm square V. Another way to write this term is norm square W. Okay. Plus this thing. And clearly this is less equals norm square V plus norm square W. Well, the real part of any complex number is less equals its modulus, which is less equals, but by Cauchy-Schwarz. This is Cauchy-Schwarz here. Plus, so plus norm V, norm W. twice. So there's a 2 here. I keep the 2 and then I do norm V norm W. And now what is this? This is exactly the right hand side square. The right hand side was norm V plus norm W. So yeah. So both sides, left hand side and right hand side, were non-negative real numbers. The square of the left hand side is equal to the square of the right hand side. And that again proves the inequality. How when does the equality hold? Oh my god. Oh my god, yeah. So please, the statement of the triangle inequality should just be the inequality. That's the end of the theorem. And yes, please delete the equality part. Okay, please delete that equality part, because even 2 plus minus 1, even though they are proportional by real numbers, the absolute value is not equal to mod 2 plus mod minus 1. I don't even know what I was thinking. But anyway, please delete that equality part. That is obviously false. So anyway, we just need to do the inequality. You can do something more, but I don't even want to do it. That's fine. Okay, so that's that. Those are the basic properties of orthogonality. Okay, very good. Okay, so now we have defined okay, those are the basic properties of inner products. Some more basic properties. So Cauchy-Schwarz, triangle inequality, Pythagoras theorem. Yeah. And so now let's go on to orthogonal sets. We've already seen definition of two vectors being orthogonal. Now I'm going to define k vectors being orthogonal, or in fact an arbitrary number of vectors being orthogonal. Okay? There is no limit on how many. I can have an infinite set of vectors being orthogonal. The idea is just that the inner product between any two distinct vectors is zero. Okay. And do I want to say what next after orthogonality? I guess basic properties of orthogonality, and we will do Gram-Schmidt. So yeah, so let's do that. Oops. And these erasers are the strong problem. They start to disintegrate very soon. Okay, so orthogonality. We've already seen, as I said, two vectors being orthogonal. Now a subset of an inner product space over a field R of C is orthogonal if V is perpendicular to W, meaning V bracket W is 0. Whenever V and W are distinct elements of that set. For all V not equals W belongs to S. I think that's the only definition I want to take. Oh, one more. We say, I mean, I don't think I will actually use it, but you of course will see this definition in many other places. So we say S is orthonormal if S is orthogonal and the norm square of norm of V is 1, unit length, normalized for all V in S. Or in other words, a convenient way to write this is the inner product of V and W is equal to delta V comma W, the Kronecker delta, what does that mean? It means it's 1 if V equals W and 0 otherwise. And this is true for all V and W in this. That's the definition. Okay, fine. So now, examples about orthogonal sets, not just two vectors. Which ways? The standard basis in Rn or in Cn is so nice. It's not just a very convenient basis, it is also orthogonal. In fact, orthonormal. The standard basis. Of f to the n, by this Rn of Cn, let's say Fn, is orthonormal. That's an orthonormal set. Second, similarly, I mean, so if you have Fn, then maybe I can say more generally, look at the elementary matrices Eij, 1 less equals I less equals M, 1 less equals J less equals N. This is an orthonormal basis of the matrix, space of matrices. Let me give you another example. So now this like we did this one, it extends to matrices. It also extends to infinite sequences. The set En, which is these zeros till the first n minus 1 places, 1 in the nth place. Sorry, where n bigger equals 1. Is not an orthonormal basis, but at least an orthonormal set in first two were bases. Yeah, but this is an orthonormal set. How should we put it upstairs? In the square summable sequences. And what about in the continuous version, in the square integral functions? Let me give you a very nice orthonormal set here. Again, it's not a basis, but it's sort of a complete orthonormal set, whatever that means. The set, the first is the function identically equal to 1 on 0, 1. Okay, I should say is an orthonormal set. I'm going to say something more here. Your n is bigger equals 1. Orthonormal set in L2, 0, 1, let's say R. This time I'm choosing R, not F. So I'm not choosing complex numbers. This set, which is cosine nx, I think I have to divide by square root 2 or multiply by square root 2 or something. Square root 2 times. Root 2 times cos nx and root 2 times sin nx. all n bigger equals 1. So look at these two functions for every integer. Root 2 times cos nx, root 2 times sin nx for all n, and the constant function 1, which is basically n equals 0 here, but I don't put a root 2. Okay. All of these guys together form an orthonormal set. And this is in fact the basis of, basis in the, not in the linear algebra sense, but this is the foundational set that you require, obviously, of Fourier analysis. Okay, so these are some examples of orthogonal sets. Again, let's talk about a couple of basic properties. This is the basic properties lemma. As usual, V is a unit product space. Okay, so now let's write down some properties of orthogonal sets. I need some water. Okay. Okay, good. We are just past the time. We have about 20 minutes left. 25 minutes left of the fun. So I will definitely not be able to start on the adjoint this time, but let's see. Let's continue. So, okay, first of all, I said that a subset is orthogonal if this happens. Well, fine, I'm not saying any analogies, but yeah, in some sense, it's pointing in two different directions. And if you think of these as like analogous to two different eigenspaces, you understand that these things are linearly independent. And that's what happens. Every orthogonal set, if you remove the zero vector from it, because the zero vector can be also trivially added to any set. But if you remove the zero vector, then every orthogonal set is independent. Okay, one. Draw better. If S contained in V minus the origin is orthogonal, then S is linearly independent. Second is what? Suppose now S is a finite set. S equals V1, V2, Vk, and none of the Vk's are 0. Is orthogonal, so I should say orthogonal. And Vi is not equal to 0 for all I. Vi is non-zero for all I, the symbol for all. Okay, then if you take any vector, so of course these are linearly independent by the first point. Therefore, if you take any vector in the span of this set, any linear combination of this set, then of course those coefficients are unique because that's linear independence, right? But the point is, if these are also orthogonal, I can tell you exactly what the coefficients are in terms of these Vi. I know a priori, you don't know a closed form expression. You know that there exists some unique scalars, Ci, such that V equals summation Ci times Vi. I can now tell you what those Ci's exactly are. Okay, so let's write that down. If W, let's say W is in span of S. If W is in the span of S, then W uniquely equals, let's say uniquely, what is it? It is summation, as I said, I need to tell you up to K. I goes from 1 to K, something times Vi. What is that scalar? Well, the scalar is, I believe it is, oh, Jesus. It's I think VIW over VIDI. Yeah, except for I don't know why I put in J's here. Okay, that is the definition. That is the formula. Is there a third part to it? No. Okay, so let's do this. Proof. Okay, so let's start with this. It's linearly independent. Suppose it is, or suppose the linear combination is 0. Right? Then you want to show that the coefficients are 0. Say summation Ci, Vi, I goes from 1 to, let's say, k is 0V, where Vi belong to S and Ci are scalars. What do? You take the dot product, take the inner product with any Vj, any of the Vj's. Applying let's see, should I do it this way? Why not? Yeah, sure. We obtain, we have summation. So, first of all, this is 0, right? So that means that taking dot product of anything with 0 is 0, that we already saw. So 0 equals Vj and then summation Ci Vi, because this was equal to 0. But then again, because this is linear in the second coordinate, I don't even take conjugates. Ci, Vj, Vi. But now notice that these are all orthogonal. I should maybe have said applying Vj for j between 1 and k. Okay, but now these guys are orthogonal. Therefore, this is always 0 except when j equals I, when I equals j. So the only term that survives is I equals j. And then this is Cj. And then you get Vj, Vj. But now here notice again also that not only is this orthogonal, none of the vectors is 0. That means that this Vj, Vj is the norm square of a non-zero vector. So this number is strictly positive. This is 0 equals Cj times this, so you can divide out and say Cj equals 0 for all j. And that's exactly what we wanted to prove. Starting from this combination is 0, we prove that every coefficient is 0, so it's linearly independent. Okay, next. The next part is to actually derive the formula for the coefficients. Because they are independent, you can now say that there is a unique coefficient and you want to answer what it is. It's the same thing now. Okay, so the same exact form, same exact proof. Start with the combination, say W, right? So W equals summation Ci Vi. Again, apply Vj. I won't even write the for 1 less equals j. We get that Vj comma W equals summation. I'm going to skip a step and not do Vj comma this. Vj comma, so I'll directly use Ci. Vj comma Vi. I'm skipping a step, but right now you guys know what that step is. It's the exact same calculation. Again, everything here is 0 except the jth term. So see Cj, Vj, comma Vj. And therefore, you know what Cj is. Cj is this divided by that. And that is exactly what is written here for this is written as Ci, but that's the same thing. Okay, so that's the end of the proof of this level. So you know these exact coefficients. And where do these exact coefficients get applied? They get applied in the Gram-Schmidt orthogonalization process. So that's the next theorem. How big is the statement? I can probably fit it in here. The Gram-Schmidt process or the Gram-Schmidt orthogonalization? The theorem says, let me write, see what notation I've used. Suppose, say W1, W2, Wk belonging to an inner product space are linearly independent. Suppose I start with a linearly independent set, but not necessarily orthogonal. It is just some linearly independent set. Then I can produce an orthogonal set with the same span at every single step. Then there exists V1, V2, Vk. In V, the same number of vectors, such that, orthogonal, the whole point is they're orthogonal, and such that. So orthogonal is that visible? Orthogonal? Yes, very much so. And such that the span is equal at every single step. I think that's all. So that the span of V1, the span of V1 is the span of W1. The span of V1, V2 is the span of W1, W2. And you keep going. The span of V1 through Vj is the span of W1 through Wj for all j less equals k. That is the Gram-Schmidt theorem. Of course, for the undergrads among you, you have already seen this theorem in UM 102, I guess, or UM 101, one of these two. I think 102. So I won't actually prove it again for you in this class, but I will write down the formula. We are saying there exist these things, but remember, because of this nice orthogonality condition, one can really write down explicit coefficients. So I'm just going to write that down. Okay. I won't mention the proof except for what the formula is, and then it will be up to you guys to check if that works inductively. You have to check two things. First, you have to check that the set I give you is orthogonal, and then secondly, that the set satisfies this condition. Right? There exists a V1, V2, Vk in V which satisfy two properties. First, they are perpendicular to each other. Second, their spans are equal. So I will just tell you what they are and leave it to you guys to verify. So proof omitted, but here is the formula. But V1 first of all is W1, and then define inductively. So having defined V1, V2, Vj minus 1, I think you can define Vj is Wj minus, you remove all the part that is coming from the Vi's. I guess I equals 1 to j minus 1 probably. Yep. Now this. So Vj, Viw over Vi, Viwj. Sorry, you want to start from Wj. So that's what you Viwj over Vi. But you see, all the lower Vi's inductively have already been defined. And so I'm using the previous Vi's, Vj minus 1, to define Vj. Okay, so I won't say more than that, as I said, for Gram-Schmidt. Of course, this is for all 2 less equals j less equals k. Okay, that's Gram-Schmidt. Now we talk about how much time do I have. Okay, I still have 10 minutes. So we'll talk about the orthogonal complement to a set and prove the proposition, and then we'll stop. Yeah. Okay, so definition, the orthogonal complement or the ortho-complement. So the orthogonal or ortho-complement to a subset, not just a subspace, but to any subset S contained in V, obviously inner product space, is defined to be or is denoted by S per. This is called S per. The definition is precisely the set of vectors in V such that V is orthogonal to S for all S in S. Yeah, that's the definition of the orthogonal. This is true. This works if as long as if S is non-empty, right? Obviously, and so phi per. If S is empty, I just look at the curve space of 0, which is all of V. Okay, so okay, so that's just the definition. It's just a curve space. It's something that's perpendicular to everything. Now there's a lemma. There's a standard obvious lemma, which is that for every subset, whether it's empty, whether it's non-empty, whether it's a subspace, whether it's half of a subspace, whether it is a finite set, any subset S, this definition always gives you a subspace. Okay, so for all S in V, S per is a subspace only. Moreover, which is again obvious, so I won't prove any of this. If you take 2 subsets, S and T, and you look at the union of those 2, and you look at everything perpendicular to them, well, then that is very naturally the vectors perpendicular to S and perpendicular to T, and so you get the intersection of 2 subspaces, which is still a subspace. The proof is check for yourself. Okay. Okay, so great, that's done. Okay, now we come to the main proposition, the last result for today. Yeah. I think yeah, we can definitely do this. Actually, maybe what I will do is I'll just write down the result and I will stop. This is a good place to stop. Yeah, because we're already at 1 hour 20 minutes. Yes, there is something. Yeah. So proposition. Okay, suppose V is a inner product space as usual. S is a set such that the span of S is finite, dimensional. It's a subspace. Right? We say S is contained in V, and the usual is such that span of S is finite dimensional. Okay. Then the entire vector space can be split as the direct sum of two subspaces. One is the spanner S and one is S perp. S perp is what we just defined here, the perp space. Right, so if you have a finite dimensional subspace basically, then you can split the entire vector space into this finite dimensional subspace and everything else. I'm not saying, notice that V is infinite dimensional. So I should say note, V may be infinite dimensional. I'm not saying that V is finite dimensional, but V may be infinite dimensional. And this is where we stop today. So we will start next time by proving this theorem or proposition or whatever. And then we will move on to other things like basically this proposition is going to help us define something called projection operators. So projection onto a finite dimensional subspace, we can do that. And then we talk about so we talk about some properties of projections. Then we talk about Bessel's inequality, and I think that is the end of inner product spaces. I mean, we will still work in inner product spaces, but that is the end of abstract inner product spaces. Beyond that, we will go on to the adjoints. And once you have adjoints, then you can talk about the spectral theorem. Okay, so let us stop here.